Okay, this will be a review for Unit 6. I should probably just go ahead and write that here. This is Unit 6 review. And I'm not really going to go over problems per se. Maybe I'll get some here and there, but I'm just going to kind of go over all the standards here. California state standards and Common Core state standards and kind of the difference between them. You'll see the difference pretty immediately. I can say it right now. California state standards really talks about the content within, as opposed to the behavior of the individual. So you'll see that this stuff talks about things that are specific in geometry. Common Core state standards, you can see this can go to all aspects of math, and it has to really do with the tools that you use in math, or the kinds of things that you do to solve problems, not necessarily the things that you use to solve a specific problem. So I'll just kind of detail both, more so these than these, and I just want to use examples of these guys so you kind of know where we're coming from with all of them. Because your exam is going to involve a lot of writing, and really it's not going to involve that many mathematical things at all. You're going to have to explain things, and they'll have questions that are based on these here. Okay, so I'm going to start with this one. I should have put Unit 6, but I'm going to start with this one, 1.0, properly apply terms, theorems, axioms, and deductive reasoning. So as you're being asked a question, thinking about properly applying terms, you can apply terms improperly quite often. For example, and this is kind of a poor example, I suppose, but if we're talking about side angle side, and you're trying to prove that two triangles are congruent, you say triangle ABC is congruent to triangle DEF, and you say by side angle side similarity. The issue here is that you're not kind of really understanding the difference between similar and congruent, and that can stem a lot further. You start looking at similarity and congruence, and I ask what the difference is between them. Well, congruence is a more specific form of similarity. Similarity is where you have two triangles and they have corresponding angles congruent and corresponding sides proportional. So if I have these two angles here congruent, and this side is 2 and this side is 4, no, they're not the same side length. However, they are proportional with everything else. If this one was 3, for instance, this would be 6. This triangle is 2 times larger than this one. It doesn't change the nature of the shape. For instance, these are both proven by angle-angle, at least that they're similar, and then you can use these sides as well to help you out. But they're not congruent, because congruent means identical, and identical means that their similarity ratio, their side ratio, instead of 6 over 3, which is 2, and so is 4 over 2. Okay, if I could get them to have a side ratio of 1, in other words, a number divided by a number is 1, which is the same number. So if I took this and changed it to 2, and took this and changed it to 3, suddenly I now have an example where I have congruent triangles. Yeah, it doesn't look the part, but that's not the point. But 3 over 3 is 1, 2 over 2 is 1. All of them assume that these ones have a side ratio of 1 as well. All of them have side ratios of 1, so not only are they similar, because by nature they have the same side ratios and congruent angles, but they're also congruent because they have equal sides, because their side ratio equals 1. So that's an example of knowing the difference, saying similarity, congruent, blah, 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 blah. So that's just getting a good example of terms, right? You see a term, you say a term, you know a term. And I could do the same with talking about alternate interior angles, right? You know what alternate interior angles are because if I have these parallel lines, alternate interior, break down the word. Alternate means opposite of, or opposite sides. Interior means on the inside. So these are angles who are alternate and interior, and by the way, these are congruent. If I were looking at same side exterior, that could, for instance, be this guy and this guy, and they are not congruent, by the way. They're supplementary. They add up to 180. You know, knowing the word supplementary versus complementary, these kinds of things are just knowing terms, properly applying them. Not just defining them, not me asking you what they are, but when you're answering a question, how are you using those terms instead of using other things? You can use other things, like for instance, and I'm probably going to use this later as I talk about it, the reflexive property states here let me get a regular line. The reflexive property here states that if I have a side that's shared in two different triangles, like this guy right here, it's congruent to itself. Now, I know that it's quite obvious. There's a word for it, which is reflexive property. And if you don't know that word, as long as you know the idea that you can set this guy congruent to itself, and it corresponds to itself in both of these triangles, then it can help you prove that triangles are congruent, for instance. But either knowing the word or knowing the idea is what's important. So not necessarily the term, but it's a much shorter way of understanding something. Okay, theorems are things that are proven to be true. It's a statement that's been proven to be true. For instance, they have proven that a squared plus b squared equals c squared in the form of a right triangle, where a and b are your legs, and c is your hypotenuse. And the square of these two sides is the square of the longest side over here. And that's been proven to be true. You can go through a proof and actually walk through it. And it's based on these things which are called axioms. An axiom is a statement that we have to just assume to be true to lead to other things such as theorems to be true. That guy Euclid, if you learn about him, for instance, he had 5 axioms that he talked about that were assumed to be true. It's called Euclidean Geometry. The first one, for instance, is saying that you can make an assumption. I hate this thing. Once I start the recording, this always pops up. Anyway, you can make an assumption here that if there are any 2 points anywhere in space or on a plane or something, you can draw a straight line through them. Okay, that's an example of an axiom. That's not something you need to prove to be true. Or when you have a circle and you're given a distance as a radius, you can always describe that circle with the center and its distance from the circle, something which we're going to talk about more in a different chapter. And there was a parallel postulate, something that says if a straight line falling on 2 straight lines makes the interior angles on the same side less than 2 right angles, the 2 straight lines, if pronounced indefinitely, meet on that side on which are the angles less than the 2 right angles. That's just something that I'm reading off a piece of paper, but that's an example of what these things are. They're things you prove. You don't need to prove to be true, but you use them to prove theorems true. And the last one here is deductive reasoning, which kind of falls in the case of theorems as well. You can decide and deduce something to be true or assume something to be true based on information given. And that's a lot of what we do here in geometry. We do court cases a lot, for example, when we're talking about them. Let's say something like that man fired a weapon. So you're going to reason with the jury that a man used a weapon with the intent to harm, right? Your deductive reasoning would be with statements. You'd lay out a statement that people use guns with intent to harm. That's a statement. And then, we have to assume some things to be true, I suppose. And then you say that this man used a gun. So your deductive reasoning based on that is saying that this man used a gun with the intent to harm. So you bring those things down there. That's deductive reasoning. Okay. There's a difference between deductive and inductive reasoning, in that deductive reasoning you always lay the things out for them to be 100% true all the time, and inductive is something that you would bring about and create based on some common knowledge about things, common understandings about things. Okay, so that's all for that right there. Write geometric proofs, including proofs by contradiction. Okay, a proof by contradiction would be, okay, well, first of all, writing geometric proofs. There's a difference between writing a proof, I suppose, and having a proof there. Well, no, it's not. Let's talk about proofs. There are 2 different kinds that we've done before, at least when I've been here. They're flowchart proofs, where you gather the facts and you lead to a conclusion based on those facts, kind of like deductive reasoning. And there's one which we're going to do a lot more, and I hope to jump into it pretty much the rest of the time. They're called two-column proofs, where you have statements and reasons, and you go down the list. So you write a proof, and you label facts. Here are the facts. This guy is congruent to this guy. This guy is congruent to this guy, and this guy is congruent to this guy. Therefore, because I have these three things congruent, I can deduce, right? I can conclude that this triangle is congruent to this triangle for this reason, blah, 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 blah. Right, so that's what that is. And same thing here, only in statements and reasons, you list a statement, you say, this side is congruent to this side. The reason, maybe it's given. And then you say, this side is congruent to this side, and then you give another reason, reflexive property, right? You do all these things and eventually come to a conclusion, this triangle is congruent to this triangle, this triangle is congruent to this triangle because of side, 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 right? So that's a two-column proof, and I just like it because you always list the reasons. It doesn't flow perfectly, that's why they call this a flow chart, because you can get all the facts going down the list, and sometimes it takes a while to go from one to the next to the next. So they do have their pros and cons in both ways, but I like us to back up our reasons and support them every single time, and then you can really tell what it is you're doing. Now, proof by contradiction is a little different. Whenever we normally prove something, we normally say, prove that these things are congruent or similar or whatever, or something. We're proving something that is already said to be true or something, and we're figuring it out based on theorems. Proof by contradiction is taking something, lending on the assumption that it's false when it's really true. You lend on the assumption that it's false, and then through your theorems and everything else, then you find out that it has to be true because of this, this, and that. I'll have to come up with an example at the top of my head here. Let's do proving that it is based on what you have, but let's say you have a right triangle and there's a statement. It says prove that the hypotenuse is sometimes shorter or can be shorter than your two legs in your triangle, something like that, right? So then you start to lay out some facts. You don't just say, well, you can use something like, oh, I already have the Pythagorean theorem, and I say a squared plus b squared equals c squared, and I know that if I take something and I square it, then it's automatically positive. So a positive plus a positive not only equals a positive, but if these two numbers are greater than 0 and I add two numbers, it'll equal a number that is greater than either of these two numbers. Therefore, this number must be greater than these two numbers. Therefore, I have contradicted my original statement that C could be shorter than any of those two guys. Right? So that's an example of a contradiction. Or something else, say, we use the idea that triangles add up to 180 degrees. And if this one is 90, because it's a right angle, then these two together not only equal 90, but neither of these can be greater than 90 degrees either. Well, they can't even be equal to 90 degrees, because if you had two 90-degree angles, then you can't get a third angle, and then you don't have a triangle. So both of these are less than 90, and they add up, they actually equal 90, but even if they added up to be greater than 90, neither of them can be equal to or greater than 90 by themselves. So what we do know is that the side opposite the largest angle is the largest side, and that is part of the triangle inequality theorem, which we'll talk about later down here. So that's another example of proof by contradiction, saying that I've contradicted our original statement that C could be shorter than A or B for that kind of reason. So that's what those things mean, and you have to do two-column proof for that or flowchart proof for that as well when you do a proof. Let me go and check these off as I go. Okay, judge the validity of a logical. Here we go. Judge the validity of a logical argument and disprove by counterexample. Okay, these are kind of more the conditional statements and their converses and stuff. And I just want you to make sure that these just make sense in a nutshell. Going with conditional, I think we had an example in one of your homeworks. If shape is a, well, let's see. I'm not sure what the actual thing was, so I'll just come up with the other one. if four-sided shape, let's say if your shape is a rectangle, then it's a four-sided shape. Okay. Okay, the way for these to kind of work here, I think you already know whether or not this is true, but the way that I kind of want you to think of these statements is you want to kind of list the properties of things when you have specific information about them. Four-sided shape is as general as you can get. I can't really think of anything else to say about it other than it has four sides and it's a shape. It's enclosed, yada yada. Now there's nothing particular about it, right? It doesn't say anything about angles being congruent, sides being parallel, sides being congruent, right angles, anything like that. So it does just say four-sided shape. Now a rectangle has specific properties, and you can start to list them as you do it. In fact, I'll give you a rectangle. I'll draw one out, and you can draw one out. Oh, that's a square. You can draw one out on your own and also do the same thing. You look at this and you say, well, what do I know about a rectangle? And that's kind of where you have to go with things. You don't have an answer listed anywhere as far as this problem, but you can access your notes and resources and figure things out. Well, a rectangle has right angles, all of them. All right angles. Opposite sides are congruent. Opposite sides are parallel. And, if it ends up mattering, diagonals are bisectors of one another. In other words, they split each other into two congruent sides. Things like that. So you take all, and a rectangle has four sides, by the way. So you take those things, and I'm just going to keep this here because I'm going to change the four-sided shape here thing later. So if I have a rectangle, do I have a four-sided shape? The answer is yes, that is true. Okay, but let's look at the converse of that for a second before I move on. And so here's the important thing about converses is that you don't change where the if goes. The if needs to stay in the beginning. I'm going to change my concluding statement with my hypothesis, but I'm going to keep the if and then where they are. I'm not going to say if it's a four-sided shape, then it's, I'm sorry, I have a four-sided shape if I have a rectangle, right? I'm going to say if it's a four-sided shape, then I have a rectangle. I should say then I have a rectangle. So it's asking, is this way true? If I have a four-sided shape, then do I have a rectangle? And the question is this always true? Not is this sometimes true? Not is it 99% true? Is it always true? And the thing about this is that when I went from this way to prove that something was true, I had to detail what a rectangle has and does. Maybe I didn't have to detail all this, but once I had to figure out what I needed, like four-sided shape, then I'm good. Okay? Here, if I want to prove it true, yeah, I'm going to do the same thing. But if I know something to be false, remember, it has to always be true. So if I can find just one false thing about it, one counterexample, then the answer is false. And that's a good thing. You can disprove by counterexample just using one example. I cannot prove by example and say that, well, this rectangle has a length of 4, therefore all do, or whatever it is, right? So disproving by counterexample here, if I have a four-sided shape, then I have a rectangle. Wrong, because I could have a parallelogram, right? I could list multiple more examples than that, but I don't have to. I've listed one. And the thing is, maybe at that point you want to say, well, what's a parallelogram? It's a four-sided shape, check, just like a rectangle. It has sides, diagonals that bisect each other, check, okay. And it has parallel opposite sides. Oh, this looks just like a rectangle, except, oh, by the way, it also has congruent sides, except there's one difference. And besides the opposite angles being congruent, just like a rectangle, they don't have right angles necessarily. Now, if they did have right angles, then yeah, it would be a parallelogram with right angles, which is also called more specifically a rectangle. So a rectangle is a specific version of a parallelogram, right? Just like it's a specific version of quadrilateral, any four-sided shape. And I can actually move on with that one. I'll go ahead and use, I'm going to take out this parallelogram and I'm going to change it to a square. Let's draw that rectangle again. If I have a rectangle, then I have a square. True or false? That's what we're going for. So this is the original statement. If I have a rectangle, then I have a square. So here, the best thing you could probably do is start listing the properties of both. Okay, so what does a rectangle have? We talked about this. 4 sides. Opposite sides, congruent, and parallel. All right angles. Diagonals bisect each other. Was that it? Yeah, let's go with that. Now square, 4 sides. And yeah, opposite sides are congruent and parallel, but if you want to differentiate one from the other, you want to be as specific for one as possible. All sides are congruent. Opposite sides parallel. And diagonals don't just bisect each other, they're perpendicular bisectors of each other. Okay. So a square is a specific type of rectangle. Yes, diagonals still bisect each other. Yes, opposite sides are still congruent. But more specifically, a square is one where all of the sides are congruent and diagonals are perpendicular bisectors of each other. So it's not true that every rectangle is a square, because you need to have a rectangle where all sides are congruent and therefore diagonals will be perpendicular bisectors of each other. But a rectangle is a square with all sides that are congruent. Now, is the other way true? And the answer is yes. A square is a specific type of rectangle. So when I list rectangle here, I'm listing these features within like this circle of here's what a rectangle is. Now a square is that specific type of one, because the ones that don't fit are only opposite sides congruent and diagonals only bisectors of each other. Here in a square, they're perpendicular bisectors and all sides are congruent, yada yada. So a square is always within a rectangle, and a rectangle is always within a parallelogram, and a parallelogram is always within a quadrilateral, etc. So if I can work from the inside out, then I have worked my converse accurately. If I work from the outside in, and a really easy example is geography, because we're looking at an actual thing. If I have California here, okay, and here's Los Angeles, okay, I can have two statements. I can say, if I live in Los Angeles, then I live in California. Yes, assuming all of Los Angeles is of California. But the converse, if I live in California, then I live in Los Angeles? No, not necessarily true, because you can fit it in any of this criteria that's also not Los Angeles. So that's the point of converses not always being true. And the way that they are true, and the conditional statements are true, is if they map 1 to 1. In other words, there is no leeway for them to be different from either thing. An example, if I have a 3-sided shape, then I have a triangle. A triangle is always 3 sides, and a 3-sided shape is always a triangle. Therefore, those are always true. So that's an example of having something that's called biconditional. Sorry, I'm undoing as we go. Example of something that I have that's called biconditional, which it's like 1-to-1 mapping. No matter what, if I go from one way to the other, or whatever, then I'm looking at the same thing both ways. And when the converse is false, that means I'm not looking at the same thing both ways. In fact, it means that I'm going from the outside in. Yeah, okay, that was nice talk on that one. Okay, prove basic theorems involving congruence and similarity. We talked about this a little bit. I'll go in just a little more depth here. I want to prove this triangle is congruent. I'm sorry, we'll do similar first. I want to prove this triangle is similar to this triangle here. Now, figures are not drawn to scale. Okay, let's say we're given that, by the way, this is called ABC, this is called DEF. Let's say that angle A is congruent to angle D, and that's given. Let's also say that angle E is congruent to angle C, and that's given. And then let's say that side BC is congruent to side FE, and that's also given. There's kind of, unless I did some matching up with these triangles, there's kind of no way to say that unless they were given. So I have A, and here I'll do this as a two-column proof. You need to look at some of those a little bit, so let's do that. Let's make this kind of look better. 2 columns. I'll have my statements and reasons. Okay, we're going to get angle A is congruent to, whoops, these are my statements. These are my reasons. Now they'll all be given, except for the very last one. Okay, angle A is congruent to angle D. Now that's given, right? They're both marked. There's no way around that. Angle C is congruent to angle E, also given. And finally, I'm not going to say these guys are congruent for now. I'm going with similarity, right? So to do similarity, I want to say that when I do BC over FE, I get 1. But because I have nothing else to compare it to with things, let's leave that alone. We're doing similarity. So right now we can say that triangle A, now this is important, by the way, how I'm going to line this up. I need to correspond angles with each other, right? This is a part of what we're going to talk about in 5 called CP-CTC. Triangle ACB is similar to triangle DEF because of angle-angle similarity conjecture. Now they're similar. I didn't say they're congruent. I don't know anything about that yet. But notice how I did that. I corresponded the congruent angles with one another. If I said ACB, 1, 2, 3, I need to go 1, 2, 3. I need to get the proper corresponding angles, D, E, F. That's why order matters so much. The 1s need to be the same angle. The 2s need to be the same angle. And the 3s need to be the same angle, which we don't know anything about. But you would know by that third angle theorem that all triangles have to add up to 180, therefore those would be congruent as well. So if triangle ACB is similar to triangle DEF because of angle-angle similarity conjecture. Now angle-angle does not prove that triangles are similar because one could be a lot bigger than the other if we didn't know anything about any of the sides. Or if we knew enough information about the sides and absolutely said they're not congruent because maybe they had different lengths of corresponding sides. However, we look at these two, BC and FE, and they are both between the second and third corresponding angles, 2, 3, 2, 3. So they correspond and they have the same length. Now you can do this 2 different ways. One, you could say they're congruent, but to help yourself out, if you don't really remember something about the other ones, BC over EF is 1. And we already know that these triangles are similar, and one definition of congruent triangles is that, oh, by the way, this is kind of given. You did the division, but the fact that you divided them is no different. Anyway, we know these triangles are similar, so they already have the same side ratios for corresponding sides. And now we used corresponding sides and found that that side ratio is 1. So if one of them has a side ratio of 1, then all of them do. And if all of them do, there's that definition of congruent triangles is they are similar triangles, but more specifically, they have side ratios of 1. So if I'm to say these guys are congruent now, I'll say ABC, oh, I'm sorry, there we go. Triangle ACB is congruent to triangle DEF by what? So here's the important thing. You can say, for instance, these are similar triangles with side ratio of 1, and in fact, that's probably what I would ask you to do if you did your proof this way. But if you skipped 3 and 4 like this, and you said here, BC is congruent to EF, you'd use one of the 5 congruence conjectures, which are side, 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 angle, side, angle, side, angle, 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 side, and HL. Now these are not just squiggly lines, they're congruent like that. You can do either or. leave them blank or put them like that. Now, how do you determine which one they are? I know you have two angles in a side, but is it angle side angle or angle angle side, and how would you know? Well, this sequence is important because it has to do with where your side is with respect to your angles. And that's how all of these actually work. When I do side, 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 I'm looking at one side, the next side, yeah. But side, angle, side, for instance, needs to be side, and then an angle immediately following, so say this one, and then the side immediately following like that. Because that one can actually be used to say that two triangles are identical if you had that matching pair in both. If I had side, angle, side way over here, then I'm not working in a sequence, and in fact, that's side, side, angle, or angle, side, side, and you know that one's not one of them. So working in sequence here, start from one to the next. You can go angle, angle, then side, angle, angle, side, or side, angle, angle. So you might want to know, because some people have asked before, is side, angle, angle the same thing as angle, angle, side? Indeed it is. All of these work backwards, it's just this is the only one. I guess HLs can also go backwards, but this is the only one that's not symmetric, right? ASA, if I work backwards, is ASA, and SAS, and SAS, SSS. HL, I don't know if they call them like hypotenuse, so to speak. They don't really call it side, angle, angle either, but yeah, this is the same because you can find angle, angle, side. So if you did the proof that way, you said, okay, here's my reasoning. Now we're going to go off the assumption that you do understand how this was determined, and we kind of did it in class. We said there's no other possible way we can make a different triangle if we're given these pairs of angles congruent and this pair of sides congruent. There's no other possible way to do it. So as long as you get that, then your reason is justified. If you don't understand that, it would be nice if you explained it somehow. So there's the concept of there's basic theorems involving congruence and similarity. I'm not going farther beyond that because we've done that a lot. I just want to make sure that the sequence made sense and the fact that similarity and congruence are two different things, and the two-column proof I wanted you to look at, all that stuff. Actually, let's go back. I want to keep that up here. Let's do (5.0) using this information. Use the concept of corresponding parts of congruent triangles. There's a thing called CPCTC. Now you're going to have to write this down because I'm not going to write it, but it means it stands for corresponding parts of congruent triangles are congruent. And what that means is, when you know that two triangles are congruent, like we have proved here, I proved this triangle is congruent to this triangle. And again, when triangles are congruent, that means they're exactly identical. They could be rotated and distorted. Like if you look at this guy here, not only is it rotated this way, but it's also flipped over, right? If I took this and rotated it that way, the side would be over here and you'd still flip it around. So it's transformed, but there are still corresponding sides. I can get BC with EF. I can get angle D with angle A and angle C with angle E, right? So they do correspond. Anyway, all corresponding parts of congruent triangles are congruent. So I already know these are congruent. These were given things. But now that I know that the triangles are actually congruent themselves, that means that if I can locate all the different corresponding parts, those are also congruent. So for example, even though I didn't know that angle B and angle F were congruent to start with, and even though I could have deduced that, remember deduction, I could have deduced that by saying if this is congruent with that and this is congruent with that and all triangles add up to 180, then this must be congruent to that because there's only one possible value for both of these that would add up to the same amount, right? So I could have figured it out that way. But another way I can figure out that these are congruent is saying if these two triangles are completely congruent, and if these two angles correspond, right, they're 3 and 3, the third angle that I listed, then these two angles must be congruent, like this and this. Likewise, the segment between angles A and C, right, this 1, 2, the segment between 1, 2, segment between 1, 2, I have no markings which say that these are congruent. And I didn't have anything to say that these were congruent beforehand anyway. However, I did prove that these two triangles are congruent, which means they are identical. And if these parts correspond, then these two must be congruent. Now, this was determined after the fact. In other words, I am reasoning this based on the fact that these two triangles are congruent. I didn't know it beforehand, and I couldn't have said anything about these beforehand until I knew that particular information. And same thing with the between angles AB and angles, is it DF here? 1, 3? No. Angles, yes, DF. This segment DF and AB, these are also congruent because they're the corresponding parts between sets 1 and 3, 1, 3. They correspond in congruent triangles, and they are congruent. Okay. Another way to put that, we talked about this with the with that murder case we're talking about. We're saying that, right, you might question whether the guy actually shoots with an intent to harm or intent to kill, right? The witness says, the defendant claims that he did not shoot with the intent to kill. Okay? Let's say he claims that. Now, we don't know whether he's lying or not, right? We don't know either way. But once you gather the evidence and you convict him of, or you say he's guilty. You say he's guilty of murder, blah, 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 blah. You're basically insinuating that because he's guilty of murder, then he used that with the intent to harm. He used the gun with the intent to harm or intent to kill. So you're going back on something that you didn't know beforehand, but because you gathered enough information to prove to yourself, or to be convinced enough, and you better be convinced to convict somebody of murder, by the way, but to be convinced that somebody murdered somebody, then you are saying that they used the gun with the intent to kill. Right? That's pretty much what that means. Okay? So that's how you go back and you correspond something. Okay, know and use the triangle inequality theorem appropriately. There are only two things I'm going to talk about with the triangle inequality theorem, and I think they're really the only two that you would need to be concerned about regardless. There are things like law of sines and law of cosines, and those things you can actually derive. It takes you a while, and I hope you already did that thing in class. But I'm going to go off that and omit that for now. Let's do, I'm going to draw 3 different side lengths. There's this guy right here, and bear with me, I'm going to draw a guy right here. Let's assume that's another side here. And I can draw a third guy. If I make this exactly that length, like exactly that length is that, but I'm going to make it a little bit shorter. Whoops. Let's do that again. I'm going to make them a little bit shorter like that. Now, I have 3 lengths, and I want to make a triangle out of these 3. Here's the easiest way for me to do this and manipulate it. Go ahead and try it first. Well, can I rotate this? Flip, order lock. Well, I guess I can't. So just pretend like I'm able to rotate this guy. I'm just going to transform him a little bit. But let's say I took him and I was rotating him down there, right? And I take this guy here, and I need to attach it at the end of this other side here. And I can take him and rotate him. I know it's a little smaller, but the fact remains, I can't get these other 2 guys to connect. I can try and go as low as possible, and just, well, try and connect them together, but they just don't reach. So one of the triangle inequality theorems, as you can imagine right now, is that if I have 3 lengths, the sum of any 2 of them must be greater than the third side. Now, hang on a second. You think about that. I'm going to take a drink of water. So I have these 2 lengths right here. Now, they're shorter than this third one. That's fine if they're shorter, but the sum of them needs to be longer. You can tell this is obviously shorter. And the reason is because I can't take these, bend them upward or downward, and connect them. Now, I can do that, hopefully, trying to, with this guy. I take him and I bend him upward. And then I try and say, well, can I take this guy now and connect him back down there? No, I can't. I'm still having trouble. Right? So you revert back to beginning. So it's impossible to do it this way. Now, you might ask, well, what if they're equal? what if this guy and this guy are equal to the length of the third guy? Well, that's all good and dandy. You can connect them at the end, but you can't make a triangle. I'm going to change the colors of these. I'll make that one brown, this one blue. And I go down here, and I start at the end there, and I start at the end here, and you'll see I can't make a triangle because I can't bring it upward. The second I bring it upward here, it starts to cause a disconnect. I can't connect them still. So these have to be longer. Let's take this, and even if I make it just a little bit longer right there, now I can take him, rotate him downward, right? Bring him up here, and this guy, take him. Let's just shorten him anyway. I mean, look how much I can still shorten the guy, and I still make a triangle. It's still not as skinny as it can be. But I can only make a triangle if the length of any two sides is always greater. The sum of the length of any two sides is always greater than the third side. Now it's not just this side. Let's take all these and let's give them lengths. 4, 7, and 9. Whoops. 9. Okay. 4 plus 7 is 11. 11 is greater than 9, so we're good. Now you have to double check everything else. 9 plus 7 is 16. That's greater than 4. And 4 plus 9 is 13, and that's greater than 7. So we're good in all facets. That needs to be true to make triangles. If any of these are shorter, then it doesn't make a triangle. And that's kind of the reason behind it. So that's one of the things you need to know about the triangle inequality theorem. The other thing that you'll need to know is if I have a triangle, let's take this and get rid of it. And I talked about it before. I said I'd talk about it. But if I have a triangle and assume, it's called the triangle inequality theorem, so assume all lengths and sides to be not equal, right, not congruent. I have these lengths A, B, and C. Don't assume anything to be a right angle. I'm not saying that's 90 degrees. And this is triangle, by the way, A, B, C. And it's important to have this opposite that, capital letters, because that's how they work. The triangle inequality theorem says that there's a relationship between an angle and its opposite side. So there's a relationship between this angle and this side, this angle and this side, and this angle and this side. And the relationship isn't exactly proportional. Like if this is 90 degrees and this is 45 degrees, this isn't twice this length. There's actually, you can use law of sines to figure out what they are. But there is something that says if angle C is greater than, the measure of angle C is greater than the measure of angle A, then side C is greater, so length AB, right? Side C is greater than side A. So if I have a larger angle than any of these two guys, then this is the longest side. And there's nothing else to say about that. If this is the smallest angle, then this is the shortest side. And therefore, this is the in-between angle, and this is the in-between side. Now, I don't know what these side lengths are. In fact, I don't know what these angle measures are either. But that's kind of how you work that out and you figure that out. You have information. You say, well, which one's longest, and whichever one's longest, I have the largest angle there, opposite it. And this is an example of something whose converse statement is true. I could have said, if C is greater than A, then measure of angle C is greater than measure of angle A. Okay, they do work conversely. So the converse is also true there. All right, so those are the two things I want you to know about triangle inequality theorem. I mean, there are other things you want to work with those, but that's kind of how those make sense. Okay, use theorems involving parallel lines cut by a transversal. I'm going to kind of jump into this in the long-standing fashion and see if it can make sense to you. This is what I'd want you to kind of do when you create this, but bear with me here. If I have two parallel lines, okay, right now the only thing that I know is that these two are parallel, all right? And that's, by the way, that's part of the parallel postulate thing, saying that lines are parallel. If lines are parallel, then they will never intersect with one another. Therefore, if lines will never intersect with one another and they grow infinitely, then they are parallel. If you have a third line, which is not parallel to them, not only will it intersect with both of them, but here's also one of those corollaries, something that's just assumed to be true. If you draw the same, if it's the same line that's crossing these two parallel lines, these must be the same angle. These two guys right here. Excuse me, I'm going to drink more water. So these two red guys must be the same angle. Same with any others in that same fashion. These two green guys right here, and then, you know, these guys down here, whatever. These are called corresponding angles. They both are the same angle and they correspond with one another. They're just in a different place, right? Because these are technically the exact same line, just in a different place. So these are called corresponding angles and they are congruent. Let's do this right here. Now, you can also say something like, okay, if those are, then these are also corresponding angles and they're also congruent. But not only that, if I have this guy here and this guy here, here's something else to be assumed. These are straight lines, and these guys, I mean, they gave them a name, but they call these vertical angles. The angles that go opposite one another here are also congruent. I don't really know how else to prove that to be true. Now, you cannot prove by example, though. Remember, I talked about this right here. You can only disprove by counterexample. I can't prove by example and say, well, there was one time when I did a problem, this was 60 degrees and so was that. Therefore, every single time they're congruent because of that one time, right? Because, but you can disprove by counterexample. Let's say the vertical angles weren't always congruent, and you said, well, because there was this one time where one was 70, one was 60. And if one was 70, one was 60, then they're not always congruent. Yeah, that's true. I disproved by counterexample there. Unfortunately, that's never true in this case. But yeah, these are both congruent as well. So vertical angles, let's do that green. They're congruent as well. And I'll just put some green in there. So if this is congruent with that, and this is congruent with that, and this is congruent with that, and this is congruent with that, now you can start saying some relationships on all these things, because these are all the same angle. This, and this are all the same angle. So now you can start saying things about these two guys, right? So this is deductive reasoning. This is saying, well, if these pairs are congruent, and these pairs are congruent, then these pairs must be congruent, right? So now you can start doing some other things here. These, we decided to say, well, this line transversal decides whether we're on one side of it or the other. If we're on opposite sides, then we'll call those alternate. They're alternating sides. And if they face on the inside of the two parallel lines, we'll call them interior. So we'll call these guys alternate interior angles. Okay? And they happen to be, I'll put AIA, but alternate interior angles happen to be congruent. Same thing with these guys, which are on opposite sides of these, and they are going on the outside. If they go on the outside, we'll call them exterior. So these we'll call alternate exterior angles. And alternate exterior angles are also congruent because of all these right there. So we have four sets of things which are congruent: corresponding angles, vertical angles, alternate interior, and alternate exterior. Okay. Now you start to play with this a little bit more, and you start to see some other things and notice them and say them. So we have a straight line here, and it's cut by the line transversal. Now a straight line can form within a circle, and within this circle I can draw half a circle there, and this is 180 degrees of the circle. If that's 180 degrees of the circle, then you can imagine that a line is kind of something with a 180 degree angle, right? While this could be 60 degrees, the entire thing is 180. So let's go ahead and draw, let's go ahead and draw this entire thing, and let's say that's 180. If that's the case, then all the angles formed within this, on this side of this line, the sum of them also must equal 180 degrees. Now we only have two angles here, so the sum of these two angles must equal 180 degrees, and we want to call these two angles something. We want to give a relationship to these two guys right here. So let's do it. Let's say these are called, well, there's this term called adjacent, which means nearby, so we'll just call them adjacent angles. I guess that's what they determined when they said that. And they said adjacent angles are supplementary, meaning they add up to 180 degrees. Now, if that's the case, if this guy plus this guy is 180, and this guy is equal to this guy, because they're alternate interior angles, then that must mean that this guy plus this guy right here also equals 180. What color didn't I use? Kind of used them all. Let's go with black for one. Then this guy plus this guy must equal 180 degrees, because this is equal to that, and this plus that is 180, blah, 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 blah. So this is kind of how you figure these things out. It's not just up in the air, and it's not just, memorize and guess and check. You can figure these things out by going off the your original corollaries. Now these are on the same side of this transversal, and they both direct inward. So we will call these guys same side interior angles. And they are supplementary. Now, going along that notion there, let's keep going. Well, if this is a straight line, then this guy right here plus this guy right here also must equal 180 degrees. So I'm going to go and add that angle. It's barely seen. Probably should have used a different color there. Now, if corresponding angles are congruent, if this guy equals this guy, and if this guy plus this guy is 180, then this guy plus this guy is 180 as well. We will go ahead and we will call those same side exterior angles for the same reasons why we're calling everything else as they are. And those are also supplementary because they also add up to 180 degrees. So you can kind of understand here how all of these come to be. And I am not sure if I'm leaving anything out. I sure hope I'm not. But I have all of these guys right here in alternate interior, alternate exterior, same side interior, same side exterior, vertical, corresponding, and adjacent. And they are all what they are, congruent or supplementary, based on parallel lines being parallel lines. Now, if these aren't parallel lines, the only ones that are true then are vertical angles being congruent and adjacent angles being supplementary. All the rest are dependent on the fact that parallel lines are existing. Because the other ones don't have to do with both lines, it just has to do with one set of lines. So make sure that you use and you know those theorems and you understand them. Okay, finally, use the Pythagorean theorem to find missing sides of right triangles. Now that's pretty straightforward. I don't think I need to dive into that too much. There are some things I can throw out at you as a bone. But I do want you to understand what HL means as well, hypotenuse leg. And that theorem, I do have a triangle shape. Let's go ahead and do it. Hypotenuse leg theorem says if I have two triangles, let's go ahead and distort this guy so it doesn't look so obvious. Take this guy, flip it. Okay, well, I have these two triangles here, and I want to say whether or not they are congruent. Now, right now, I don't have any other information other than they are right angles, right there and there. And in fact, let's really screw with you here. I'm going to make this a right angle. Does it look like a right angle? Absolutely not. But guess what? Figures are not drawn to scale. Now, if this is a right angle, I don't know if I'm going to screw you up with this, but if this is a right angle, then this is the opposite side, which is the hypotenuse, so this is the longest side. Now, that's something that will really mess with you, and I want you to understand that because I can trick you on a test like that as much as I want. You have to trust that and not say automatically that's a right angle. So I have, I want to make it pretty easy. I have 17 here and 17 here, and then I have 15 here and 15 here. And I want to figure out if these two guys are the same. Now remember, this is a leg because this is on this side of the right angle. That's the hypotenuse. So I want to know if this is the same leg. Now here's where HL kicks in. HL says if I know the hypotenuse, if they're congruent, and if I know one set of legs are congruent, then that other set of legs must be congruent. Because if I use Pythagorean theorem, and let's say, here, let's change this into an A. Let's say we're solving for A. Well, A squared equals C squared minus B squared, just subtracting the B over. And if C squared is 17 and B squared is 15, there's no other way I can change those numbers and get a different A squared. You do the math, you get 289 minus 225, which is 64. and square root of 64 is 8. So you get a equals 8, and a equals 8 for both of them, and it must be. There's no other thing it can be, right? So if there's no other thing it can be, that's why they say that we already know these triangles are congruent. I don't need side, 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 and I know this is angle, side, side right here. This is the only exception to angle, side, side that's true when you have a right angle, because it's called HL. So just know how Pythagorean theorem works. If you need a leg, you have to subtract leg from hypotenuse. If you need hypotenuse, you add the legs together, you square them, all that stuff. Okay. Now I want you to keep in mind, there's a difference between a squared plus b squared and a plus b squared. You don't want to add these guys together first, then square it, because this is a squared plus 2ab plus b squared. It's a perfect square trinomial, and you have to FOIL, right? You have to use FOIL to do that. So those are two different things, obviously. Just want to keep that in mind. All right, so that's it for the, So that's it for these guys. I'm not saying that, boom, you've aced the test. I'm saying that at least now you have a good background of what you're looking for there. I'm sure that took quite some time. I want you to make sure that if you want access to the stuff, then you get it. You do understand it. Now, common core state standards, I'm not going to go over these with examples. I'm just going to go ahead and talk about them a little bit. And they're pretty straightforward. You know, they are what they say. Make sense of problems and persevere in solving them. Okay? If you're mathematically proficient, then you can kind of explain to yourself the meaning of a problem, right? You can make sense of it. You can make sense of that meaning, and you can look for entry points to its solution, right? You kind of already know, all right, I see what I have to do to let this problem be what it is. Okay? You can make conjectures about the form and the meaning of the solution and plan a solution pathway rather than simply jump into a solution attempt. So you're not going straight into, all right, I'm going to plug this in just because, right? You get where you're going with it. I don't really have, I don't have the parallel lines thing anymore, but I can deduce same side exterior angles by all the stuff that I did, right? I can get that path correctly, not just jump into formulas. I know what I'm doing. Or better yet, we'll talk about distance formula, and it has to do with the Pythagorean theorem. So just kind of knowing that stuff, persevering and solving for them, you know, you're really pushing through it. You're making sure that you can check it a bunch of different ways, right? I know different methods that I can make this thing work. I'm going to double check this. I'm going to say, does does my answer make sense, especially in word problems, right? If I'm looking for a height of a person and I get negative 100 feet, then I know, then I know it's wrong. I know there's something wrong with that. So just kind of making sense of, there's nothing else to say about that, really. Reason abstractly and quantitatively. Abstractly is kind of just looking at the general gist of something. Like you're going to see on your exam, I'm not really going to throw out numbers to you because I don't want to use examples. I want to use a general guideline. So I'm going to use A, B, and C, or let you generalize using A, B, and C, or these things are just congruent by tick marks or whatever it is. Just making sure that you can see relationships in problem situations, right? You can see if you have triangles that are built like this and these two are parallel, you can always deduce that these are alternate interior angles, right? You're kind of noticing that. There's no side lengths there. I don't have any angle measurements, but I'm kind of getting that based on the fact that I can quantify that in a certain way, right? I can decontextualize it. Now I know I'm coming up with a bunch of different words here, but it's kind of the words that you want to use, right? Quantitative reasoning entails habits of creating a coherent representation of the problem at hand. So, like, you're looking at the units that's being used, how many feet is something, right? If you have to convert something, not just computing, right? It's not just computing, but just making sure that you can kind of, you got different properties of operations and objects and all that jazz. Okay, so I'll check these off as I go. Construct viable arguments and critique the reasoning of others. Okay, this is the big one. This is the one that I want you to just get out of this class. If you don't get this, then I'm going to say you didn't get that much out of this class. You can tell, right? Because I want to give you chances to do things that aren't just math. And, we did the logic puzzle with the court case. And it's not enough to make a conclusion on something based on assumptions, right? You have to get evidence. You have to match them together and draw conclusions from that. Right, so the evidence thing really stacks up in a right way, and it's based on previous knowledge. It's based on resources. I understand that, but critiquing the reasoning of others is just as important. So it's not just knowing what you know; it's being able to take what they have, and critique. Critique isn't always a bad thing. Critique is also a good thing. Give feedback in some sort of way where you can kind of acknowledge what they used, know how to manipulate what you had in favor for. What they had to favor your argument, or what you had to strengthen their argument, or to oppose their argument better, play devil's advocate, do things like that. How are you able to trust your gut when you need to, and not just say, if you say 2 + 2 = 4, and I as the teacher say, no, 2 + 2 = 5, I don't want you to just say, okay, yes, okay, I believe you, Back up your statement. I'll back up my statement, you back up yours. It's going to be hard for me to back up 2 + 2 = 5, right? But that's kind of what I mean by that. That has to do with the converse stuff, right? I tell you every rectangle is a square. You tell me that's false. And I say, okay, why? And you can't come up with a reason. You just say, well, whatever. Well, actually, I'm sorry. Let's not do that one. Because you can just say, well, here's an example of a rectangle that's not. That's disproving by counterexample. If you say it's true, and I say, okay, why? You have to, and you can't come up with a reason, well, then that's not much help. You need to break it down and say, well, here's what I know about a rectangle, and here's what I know about a square, and based on only what I know, all of these are the exact same. If that's true, then okay, you've given as much as you possibly could. You might have not had enough evidence. If you can get more, that's awesome. Model with mathematics is a little bit more in terms of like the dodecahedron calendar thing that I gave you. How are you able to see something in 2 dimensions, fold it in the appropriate way, and make it into a 3-dimensional object, right? How am I able to go out into the softball field and project what kind of angle I need to hit this ball at to do whatever else? Kind of real-world applications. There's sometimes here I'm going to give you examples of model with mathematics things. They won't be real-world applications, but how are you able to use your math and expound on it in a way that you didn't use it in class, like in those actual problems that we've done before? So how are you able to do it from new problems, kind of? Use things that way. Use appropriate tools strategically. We're thinking in terms of calculators, your textbook, rulers, compasses, protractors, I don't know, cylinders, using appropriate tools. I said textbook, I mean, using your different resources, kind of, attach things in a certain way so that you know how to, my internet forum, my central hub, the thing you're probably watching this on. Using those in a certain way where you can help yourself against all odds when you're kind of limited or handicapped in a certain way. Okay, attend to precision. This one's kind of important because this is the difference between math and not math, right? I told you guys, if you looked at these two things, you would say this is the right angle. And I'm saying, you don't go based on what you look at, because appearances can not only be deceiving, they can be completely wrong, right? You can see, look at all the optical illusions online. Go to Google optical illusions. You'll see, is this shaded area darker than the other one? Based on how they make you manipulate your mind, you'll say that they're different, but they're really the same. Or is this person smaller than this one? And it's just, it's just an illusion. So attending to precision is really about using the numbers and the figures in such a way that they're handed to you and you can make a note of that. Not only that, but when we get more into graphing, and we won't too much in geometry, but you get into graphing here and you have a line that's crossing through like this, and I want to ask what this point is when this line crosses through with this line right here. I don't want you to say what it's about. I don't want you to say, oh, it's about 2.5, 1.5, right? I guess it's about that, but it's not exact, right? These must have equations somewhere. Y equals negative 1/2 x plus 3, and y equals x minus 2, right? How do you figure out that x and y? Set these guys equal to each other. Use actual math, and then you figure out what that thing is. Now, who knows what that is in the end, but, so hopefully that makes sense. Actual precision. You cannot you cannot miscalculate things, right? I'm not saying if you want to be a rocket scientist, but rocket scientists cannot be off by that slightest decimal place, otherwise, the rocket blows up, right? There's so many things you have to be precise about and you have to make sure of and just be positive with. Okay, I shouldn't be checking this off before I do it. Look for and make use of structure. Structure can mean two different things. Structure can mean this kind of thing, the visual, here are my right triangles, whatever. Here's, the fact that they're right triangles, that's something you know about the structure. And things with, once again, we'll take the shape again, parallel lines, make use of the structure. And you say, by the structure, these are alternate interior angles, etc., vertical angles. Excuse me, but there's also the structure, like in a formula, like these two guys right here. What's the structural difference between a squared plus b squared and a plus b quantity squared? And it's that, well, there's these parentheses, and these are grouped before this. So you add this before squaring that instead of squaring that adding. And there's a difference between the two. That's mathematical structure. I'm definitely thinking in terms of PEMDAS, order of operations. Ranking exponents in terms of degree, right? So, probably try and get the highest degree first whenever you can for your leading variable. Those are things in terms of structure. I don't really know how to go beyond that right now because I kind of want to wrap this up. Finally, look for and express regularity in repeated reasoning. And by that, I kind of mean like, when you get into CP/CTC or something like that, then you're really just trying to get, how do I say it? If you do congruent triangles enough and you kind of figured out on your own what CP/CTC was based on what you did, well, then you end up CP/CTC is what it is. You found out that this side was congruent in the end, despite the fact that you didn't know those sides were congruent in those two triangles, all that stuff, right? I know all that talk's kind of going over your head, so I'll try to think of another example. It's basically you recognize a pattern and you assume that something is true based on that pattern being true over and over and over again. Now, you don't want to say it's true. You can make some general assumption about that as you keep doing it and as you go. For instance, you do numbers and you divide them by 5, right? You're taking, hey, what happened to my other guy? Well, I guess it's just looking like a mouse now. Let's see if I can get that back. I guess I can't. Okay. Good thing I'm wrapping it up. You take numbers and you divide them by 5. I do 2 over 5, I do 5 over 5, I do 7 over 5, I do 10 over 5, I do 25 over 5, 39 over 5, etc. You divide and you're saying, gee, anytime I divide by 5 and my number is not a multiple of 5, which is kind of obvious, but it's not, but it doesn't end in a 5 or 0. How about that? I take numbers and they don't end in a 5 or 0. I'm getting a decimal. That's kind of weird. This is 1, this is 2, this is 5. All these are decimal numbers. So therefore, I can probably reason that I have to take a number that ends in a 5 or 0. Now when I divide it by 5, or I'm sorry, in the units digit, the ones digit, it ends in a 5, and when I divide it by 5, then I'll get a whole number. When I don't divide one of those by 5, then I'll get a, when I divide a number that doesn't end in 5 or 0 by 5, then I get a decimal. Something like that, right? You do something enough, you get some patterns, and you get repeated reasoning. You do it regularly, you'll find things out on your own in this class, and that's something that I want you to do. It's called discovery learning. If I was teaching Algebra 2 trig, or Algebra 2 or whatever, you'd be doing it a whole lot more. We kind of have to do it a little more slowly here and walk through things together because they're always brand new. But that's kind of what that means. And you do this in all your math practices, so this isn't just for geometry. Okay, we've checked everything off. And I could have walked through more examples, I suppose. And if you have more questions on these things, you can always ask. These are kind of more implied, so it's not really something that like, oh, this happens this way. But these are things where you have to kind of know them. And that bell rings. That might be my cue to go here. I hope this made sense to you. I hope this helped you out in some ways. And if you do have any questions, go ahead and shout out and ask them.